Brad, thank you so much for joining me today.
Yeah, nice to be chatting.
Let's start with the fundamentals. Can you explain the idea behind collaborative robots? And also, how do you distinguish or where's the line between just a normal robot and a collaborative robot?
Sure. The idea is that when I was at Amazon, we led their robotics expansion. We took advantage of a lot of the structure that exists in those environments. Um, Amazon innovated in pouring very flat concrete floors. And we were able to fence in robots and it just we need robots everywhere. And I think the pandemic really kind of showed us the fragility of our labor system and our supply chains and our logistics infrastructure uh, that leads us to need robots in more spaces than just in Amazon warehouses. And yet, the challenge of deploying robots into all these spaces is that you don't have the freedom Amazon had to design new buildings or new process paths. You need robots that can work in and around us, and generally in and around humans. Um, and so the idea behind collaborative robot or collaborative robotics is how do we bring a new type of mobile collaborative robot into the world around us that can work in lots of different commercial environments, from warehouses, logistics, manufacturing, but also hospitals, airports, stadiums, um, and have something that's has human level capabilities, particularly in the area of moving, material movement, boxes, totes, and carts, um, without needing the complexity of a humanoid, but with something that's quite a bit more capable than today's traditional mobile robots, which are generally very very low profile, generally depend on fairly flat floors. Um, so that's the idea behind collaborative robotics. I think that where, to me, when I think about collaborative, I think there are multiple levels of collaboration. There's side by side work, there's turn taking work, there's joint work, um, and ultimately, I think robots are going to do all of that. But the progression right now is from kind of where side by side equals fenced off and in a different space to side by side means sharing the same space that humans share, and then ultimately progressing to more turn taking, more joint work. And I think our thesis there is that the robots need to have an understanding of what the humans around them might do, but also humans need to have a reasonable expectation of what the robots might do. And so that collaboration uh, comes down to a lot of expectation setting, a lot of expectation management.
That's amazing. And you've published a wonderful set of articles describing your vision around collaborative robots or cobots for short. I want to dive into that. Um, First, you've talked about the concept of building blocks in robotics. So, can you explain what these building blocks are, and also how do you see these blocks being deployed in practice?
Yeah, I think about building blocks. Um, I think so. We often start from like, how do we automate a particular process, right? And maybe that process is, you know, bin picking, an item from a tote. That's one process building block. Maybe the process building block is sorting something. You have something, you want to put it in multiple different bins or destinations, right? Maybe that process is moving a pallet or loading a pallet onto a shelf. What what we then do is we start to think about how do we compose those different processes as we automate them. How do we go from unloading something from a truck to taking that pallet to sticking on top of of a shelf to then bringing that pallet back down from the shelf to taking the boxes off the pallet to unloading, extracting the things out of those boxes, packing them into a new box, shipping them out, right? You can draw a whole process map. When we talk about building blocks, the question is how many different mechatronic technologies are you going to need to do all of that, right? And what I just described, you might need, an autonomous forklift and an autonomous, palletizer and depalletizer, and something that can extract from a box. As you Our observation is that you would ideally like to have as few different robotic technologies as you can to do that. Um, the you look at other robotics companies' websites and they show this like beautiful portfolio of like 30 different robots. But the reality is like 30 different robots is 30 different things to integrate to get working together, right? And you're trying to assemble and create these process paths. Um, and then you don't get a lot of reuse, and so everything becomes a little bit brittle. It's a little bit like having a Lego kit which is all specialized pieces versus just this the 4x2 bricks and blocks. With the 4x2 brick you can build a lot, right? With the specialized pieces you can kind of build just that one specialized thing. And so when I think about building blocks, that is kind of the analogy. I'm thinking about, okay, if you think about it from Lego bricks, if I have a 4x8 brick and I have some wheels and I have a big platform, like I can build all kinds of little cars, right? Um, Versus if I just have a car kit with very specialized things, you can just build that one type of car. So that's what I encourage people to think about when they think about approaching robotic automation um, is to think about, okay, if you're going to go solve this one problem, let's say you're going to solve kitting, right? You're going to, take a bunch of things from, an inventory stock and place them into, I don't know, a box or a bag or a tote that is, an assembled set of things for a task. The You're going to use potentially a robotic arm. If you use something that is very, very custom to that task, then you're not going to take the lessons from that experience to the next type of manipulation task that you have. Where if you can build that off of a common building block, like a uh, FANUC or an ABB or KUKA or Universal Robotics arm, then the experience you gain from how to use that robot arm in there, and the qualifications you did, and the IT certifications you went through, and the staff training and the maintenance, all of that becomes leverageable in those other process paths. And then you can start to redesign your whole system saying, I've got a great building block for manipulation. We think that the building blocks for mobility, for moving human scale loads around are underdeveloped, right? They tend to be fairly simplistic. They run on very flat floors, very low to the ground. They tend to only interface with their own types of containers or carts. And so it's not a very easy building block to take into different parts of. So to take a hospital operation, they have most hospitals have some kind of warehouse where they're storing offsite stuff, and then they're bringing those up to patient floors. Well, if you have to have different robots in the warehouse than you have in the hospital, than you have on the patient floor, that's now 3 systems you've got to figure out how to manage. Whereas if you get good at one and it works in all those environments, then you're leveraging all that expertise. So that's what I mean when I say trying to be really smart about picking your building blocks so that you find robots that can work in multiple process paths, and that gives you the most flexibility over time.
With that framework in mind, how do when people talk to you about the architecture of a cobot, like how do you explain the architecture of a cobot in terms of not just saying, hey, here's the hardware components, here's the software components, but it's more like a robot has to sense its surroundings and then extract some information from it and then take an action. So in this case, how do you think about the architecture of a cobot?
Yeah, I mean, I think to a large extent, it's a systems problem, right? You're trying to bring together electrical, mechanical, hardware, you're bringing in sensing, you're bringing in compute, you're bringing in software, very low level software, higher level software. You're bringing together machine learning, AI. You're both bringing together kind of classic techniques and SLAM planning and newer techniques, maybe large language models and higher level planning. And so when I think about the architect, I mean, the first thing to acknowledge is it's a systems problem. You need to bring all of that together. Um, and then you need to do it in a way where you understand the operating environment in which the robot's going to work and how humans are going to interact with it. And so all of those things have to come together to develop the architecture. And um, I mean, uh, it's not an easy exercise to try to bring together something that's new and different. I think what we look at is, for our robot, we've looked at we want to work in human spaces alongside humans, moving human scale loads. Volumetrically, that means you're kind of constrained to the similar constraints of a human. If you want to be able to go through a door, can't be much more than 28 to 30 inches wide, right? If you want to be able to scan the environment around you, you kind of want to scan the environment from, I don't know, 5 foot 10 inches in the air, kind of the place where humans would scan. If you want to deal with ramps and bumps and other things, then you I don't think you need bipedalism, but you need some flexibility in the mobility. Maybe you need some slightly larger wheels or a little bit more suspension. So we think about the architecture as looking at the class of problems you're trying to solve, and then how do you put together a system that is best set up to solve those. And then you obviously have to bring in factors like how long will the batteries last? How, do you need to sit on the charger? How much does it cost? How much does it cost to operate? How's the reliability maintenance? So robotics is complicated. There's a lot that has to come together.
Right. Uh, and within an industrial setting, you talked about how cobots and humans, they have to be in the same space, work together, and those industrial robots, they're pretty like they're strong, and accidentally when they're moving, if you're like a second late, the arm might hit somebody in the head, and that could be catastrophic. So what are the primary challenges you encounter in like real-time interaction between cobots and humans, especially when it comes to things like this, like safety?
Yeah, I mean, I think it's really important to start from the physics of uh, the power you have in the motors, the mass you have in the robot, the ways those forces might translate into the world around, and then making sure that you have the sensing and perception, and you're kind of managing all those forces, right? Uh, we as humans just kind of naturally navigate the world without realizing that it doesn't take that much force to. I was out biking yesterday and I hit a pothole that I wasn't expecting, um, and the handlebar jammed my hand, right? And
Right.
yeah, I mean, still a day later, it's pretty sore and pretty flexible, and it's like all that was like a 2 inch pothole, but 2 inch pothole going 15 miles an hour, stiff frame, handlebar goes in your hand. Uh, you can injure yourself. So it's really critical to be aware of the physics of the system that you're building, and then to make sure that uh, you have uh, the controls, the software, the e-stop procedures, everything designed uh, with those forces in mind, so that the experience of working in and around a robot shouldn't be like, we shouldn't have to teach people that they shouldn't stand next to a humanoid robot because it might fall over. Like, we shouldn't have to teach them that. Because
Right.
you and I, if we were standing next to each other, aren't worried about one of us collapsing onto the other,
Right.
right?
Right.
And
Right.
even if we did, we're not made of metal. And so actually, if you collapsed onto me, I'd, try to catch you, right? Try to break your fall, because your fall could be harmful, but you're not that likely to seriously injure me if you were to fall. But something metal standing next to you that glitches and collapses. And so we think a lot about that, like just intrinsically, if you've got 4 points of contract on the ground, and the center of mass of the robot is over those four, then it's stable. Then it's not going. And so there's other things you can do to make sure that physics is helping you, not working against you.
Right. That's a very good way of looking at it, is just understanding the physics and starting from there to make sure that nothing catastrophic happens. And also on top of that, based on the needs of a cobot, what sensors are incorporated in a cobot, and also, is it more than an average robot, or is it the same, or maybe it's the way you process the data from the sensors that's different? So how do you think about the sensing aspect here?
Yeah, I think my general philosophy is you start with making sure you have enough sensing to give you the type of coverage that you want. You don't really want blind spots. Um, if you want to precisely know how far something is away from you, a laser scanner or lidar is far more accurate than a radar or a vision system that's trying to interpolate 3D. So, so that's how we think about it. Is we think about lidars have an important place to role to play. Stereo depth cameras have a very important role to play. 3D lidars and 2D lidars, and then you're fusing those different modalities into um, software that can then process that to determine, am I close to, where am I in the world, and how far away am I from something that I'm trying to make sure that I don't bump into. And so that's how we approach sensing, is use the right sensors for the type of understanding of the world that you're trying to get. And then over time, as you always, there's a pressure to bring down cost, right? And so over time, you may come to learn that there are different ways to cover some of those blind spots that don't require quite as many cameras. Maybe you go to a bigger fisheye camera. Maybe your need for lidar is more narrow, and you don't need as much of a 3D world, and you can then kind of bring the cost down as you invest more in the sensing and perception algorithms. But our philosophy is to start from having enough sensing that you feel confident that you know what's going on in the world around you, and you're not having to the robot's not having to guess.
Power consumption is a critical aspect of robot design. And you mentioned that you want to have enough sensing, enough compute to make sure that the robots are actually doing well. So, how do you optimize the computational load and power consumption of cobots while maintaining performance?
Yeah, so one simple thing is that it turns out the motors tend to consume more power. You know, mass acceleration. If you're moving things around the world, that takes more power, um, typically than the compute does. Now, that doesn't mean the compute is isn't material as well. It just means you have more dimensions and more factors that you can play with when trying to manage uh, the power budget. I think the other advantage to being something that's mobile and on the ground is you're not. Yeah, I've worked on drones as well. I worked on the Amazon Prime Air program, and in a drone, your weight budget is your force is you're overcoming the force of gravity, right? And so the amount of power you can put in those motors is dependent on the amount of weight, and so you're always in this this kind of tricky trade-off where more batteries would be great, but more batteries means more weight, which means more, and there's kind of an optimal point in that curve, and it's not ideal yet. We would still like to have lighter weight batteries, higher energy density at the same weight. Automobiles, we think about, oh, maybe it's the power of moving the 6,000-pound Tesla. It really turns out that, wind resistance is velocity squared, right? So the faster you're going, it doesn't go up linearly. It goes up as a square. And so that's why, it's so important that those be wind resistant or, very aerodynamically efficient. And a mobile robot, really, it's most of the power is going into how much are you trying to lift, how much are you trying to move, how far are you trying to traverse, are you going up a ramp, down a ramp, wind resistance, overcoming the force of gravity are less your concerns. And you can put higher density batteries in. So it's, it can be hard to get an hour worth of performance out of a drone battery, but it's not too hard to get 4 to 6 hours of lifetime out of a robot battery.
You've talked about zonal compute architecture and how it's advantageous over a centralized architecture. So can you explain what zonal compute architecture is, and specifically compare and contrast that with the centralized architecture?
Sure. So a zonal compute architecture is what you might imagine. It's that you have computation in different zones of the robot, right? And so, as I described in our robot, we're sensing the world from kind of human height, human vantage, and so we have an NVIDIA or an compute that is fusing all that sensor data, processing it, and then understanding the world at a slightly higher level and sharing that information, generally over Ethernet with another computer on board, which is handling the motion control and those kind of controls and systems. And then you sometimes have a computer just dedicated to lower level safety functions. If you drive a Tesla, every once in a while you have to reboot your Tesla. But that's only the console, only the display. Like, you're never rebooting the motor controllers, right? There's another layer of compute in there that is, engineered a little bit differently. You don't have to reboot it. And so that's the idea behind zonal compute, is that we can have a computer dedicated to a particular function of the robot, sensing or planning or motion control or grasping, loading and unloading carts or boxes and totes. And each of those computers has enough dedicated compute to handle the task at hand. And then they communicate with each other whatever relevant information maybe needs to be integrated between the sensing and motion control. But this is a way to subdivide the work and make sure that you're not, again, if you don't want a system where, man, your Bluetooth just failed, so your car is trying to reconnect to Bluetooth. Meanwhile, like, Wi-Fi went out and the user's pressing the radio station, and like a whole bunch of things are going on. You don't want
Right.
that to affect whether or not the accelerator works, right?
Right.
And so that's the idea of decoupling the kind of layers of the system and compute, and making sure that, and it's also a way to make sure you have enough compute on board for the various different tasks you're trying to do.
For task planning and execution, do you use AI models that are installed on the device, or maybe a combo of on-prem and cloud? So can you explain the AI models being used for task planning and execution?
Yeah, so there are, as we said, a couple layers of task planning as well, right? I mean, one level of so at the higher level of task planning is just understanding what am I being asked to do? Where do I need to go? What do I, and sometimes so we're working in a transload facility right now. We're moving transload carts. We have a vision system that detects that there's a cart in a spot that says it's ready to go to another destination, right? And so that task assignment is self-assignment. The robot notices that there's a task to be done, and then it assigns itself to go do that task, drives up to the cart, recognizes a tag that tells it where the destination is, grabs the cart, takes it to that other destination. Then it might notice that there's an empty cart in a ready to go spot and take it back. And so in that world, task selection and task assignment is fully autonomous. The robot notices there's work to be done, there's a queue of work, and it just completes it and does it. Task assignment could come from, a warehouse management system that's saying, hey, I need you to move here, there. Task assignment can also come from a human talking to the robot and saying, hey, can you grab the cart over at dock 3 and take it over to dock 9? And so there are lots of ways to instruct the task. And so each of those, the task planner is a little bit different. Like in that warehouse management example, the task planner might be kind of in the cloud, the high level one, and it's just very precisely telling the robot what to do, right? In another world, the robot's self-identifying tasks. In another one, the robot needs to understand human language, understand, if you said, hey, grab that cart over there, right? Maybe it's vision picking up your gesture, right? And saying, okay, over there looks like it's dock 3, right? Go over to dock 3, see if there's something. And so we think this high level task planning is a really, really interesting area for AI right now, because we can do far more with large language models and with these vision models, and kind of incorporate, when you say over there with that gesture, and that's what's going to make robots much more natural and intuitive, more trustworthy, more collaborative, where you don't have to be super precise in specifying exactly how you instruct the robot to do things. Then obviously at the next level of planner is understanding a motion plan, which says, okay, I see there's free space, over here. I'm gonna turn left up this little cart alley and like turn right to get to the cart, and kind of forming its own motion plan that way. So there are a few levels to the planner, but I think what we're most excited about is AI is really helping at that kind of human communication, and then resolving those interactions with humans down to, a high level plan that the robot can then go execute as a lower level plan.
That's actually going to be a huge leap, integrating LLMs into robots. And one of the first thing that comes to mind is, hey, I can talk to a robot. I can tell the robot what to do, and the robot does it. But as you mentioned, it's not as simple as humans don't talk in like a robotic instructional way. Just say, hey, pick that box over there. So in addition to understanding speech and converting that to text, that's simple, right? It's a solved problem. What reasoning problems do you encounter, or do you have to solve for the robot to feel natural?
Yeah, I mean, I think the obviously the level of reasoning capabilities in large language models is an active area of a lot of debate. But they do have base level reasoning capabilities that are quite reasonable, right? And so, when you say uh, there's a package arrived down at the mailroom, can you go get it? Being able to translate that to, okay, I should go to elevator bank 3, I should go down, I should go to the mailroom, and then I should expect that I'm going to get a box, right? Is the large language model can deductively anticipate that that's what it, and decide that that's the plan that it should follow. And really, large language models have that capability. So we're not it's not the same as like the end game in chess where you're trying to look 6 moves ahead and trying to figure out how to use space. And it's not that type of reasoning complexity, or even, now people are trying to solve these like math Olympiad style word problems. Like that's, we haven't had to solve those type of reasoning problems. And so the type of reasoning problems that we have are, there is some spatial understanding. You need to understand what an elevator is, things like that. But it turns out large language models have a lot of that capability already. I think what we're interested in is, can we give the robots more context? So, for instance, maybe you want the robot, when it's going by a bank of elevators, to go a little bit wider around, just because um, or you know what, in a hospital, people with more mobility challenges tend to go slower, and they tend to be more concerned if something's going quickly, right? And so as humans, we will almost naturally, if we can sense that there's someone who's kind of has mobility challenges, is going a little bit slower and maybe is slowing down, we will naturally slow down in kind of empathy, but it's almost subconscious. We naturally slow down with that kind of empathy. The We don't expect that, uh, a large language model developing a high level plan is going to necessarily have that type of awareness. Or it can, right? We could build vision language models that can interpret and have that kind of empathy, but the ones out of the box aren't necessarily going to be able to do that. And so we think there's, an extra layer of refinement in some of these environments that helps people I think about, like, if there's a code blue in a hospital, that not just because there's an announcement, right? You also can see how people are reacting, you can see lights, other things. And so we want robots to be able to understand the universe that they're operating in, and to be able to incorporate that into how they think about the plan. Maybe I should go around, right? You or I, if we came upon that and we're not on an urgent mission, the mail courier is not just going to walk through a crisis situation. They're going to back off, find another way around, maybe come back later. You kind of want robots to have that same level of sophistication and understanding.
Simulation plays a big role in robotics development, and going from simulation to real world, sim to real, that's always it's a challenge because not every single situation can be simulated. So, and we have tools like NVIDIA's i6 Sim and other tools to help with that. Can you describe the approach you take to go from simulation to real world deployment? And also, is NVIDIA like i6 Sim, is that sufficient, or do you have to do something additional on top of that to make sure that you catch as much as you can in simulation?
Yeah, I think simulation is an incredibly important tool for robotics, and I think the investment NVIDIA is making in Isaac Sim and those tools is incredible. And they just announced Isaac Sim 4.0, and it looks like some amazing capabilities in that. Obviously, I think that there are other tools, Gazebo, other things that work well in particular tasks, Majoko. And so we're not a kind of one simulator to rule them all. I think simulation is, um, in a lot of these ML tasks, reinforcement learning tasks, there's a phase where you're kind of exploring the policy space, where you haven't kind of got into the fast learning portion of the curve. Now, diffusion models and the attention mechanism and transformers helps you to get out of that broad-based explore phase much more quickly. But when you are exploring, it is far cheaper to do that in simulation than in the physical world. Now, the nice thing is, once you've explored and you've kind of developed a policy that roughly works, right? Loosely, or works in sim. Then refining that policy with, a smaller number of samples from the real world, and then zero shot, one shot, few shot. The reality is how quickly can you move from simulation into a policy on a robot in the real world that works well. And yeah, we're continuing to see that um, both the amount of time you have to expend in explore phase is getting less and less. Imitation learning is one of the popular techniques right now to try to get you out of that kind of explore phase and into an initial policy that's pretty good. Um, and so, yeah, that's the progression we're seeing right now. Some combination of imitation learning to reinforcement learning and sim to refinement with real world samples to transfer onto the robot. Um, there are other things just like uh, modeling out what the process flow is going to look like. We built an Isaac Sim simulation for this cart movement task so that we can make sure that the planner and before we could get into that warehouse and start doing it. So lots of different ways that you can use sim when we're developing our controllers and we're doing some of these force mass studies. We're using simulation to understand, is there a tipping risk for this robot? How, if we break this if we employ the brakes on the motors this fast, what's going to happen? And so yeah, simulation just gets used in a lot of different ways, and it's a super important tool.
And as you scale up the number of robots getting deployed, in the future, in the same warehouse, there'll be many robots. So, how do you think about multi robot coordination? Or rather, let's say there's a team that's in charge of that. What are the things they need to keep in mind while designing a system like this?
Yeah, I think the multi-robot coordination kind of comes back to our planning conversation a little bit, which is how are the robots figuring out their plan? And if the answer is there's a warehouse management system that's orchestrating everyone, which is kind of how Amazon's uh, architecture works, um, then multi-robot coordination is pretty straightforward. The warehouse management system said bring this tote over to this location. It arrives at that location. Maybe there's a sensor that says it arrives, and then it puts the tote on the station, and then the robot arm activates and does the work, and it's all coordinated kind of in the cloud. The way humans sometimes do these processes, though, is you bring the tote up to another human. The human says, "Oh, there's a tote there," and then starts doing the task. I think robots will be, increasingly able to do that as well. And so it comes to this like coordination, collaboration. How much of it is orchestrated from some, Oracle in the cloud that's planning out everybody's steps and workflows, and how much of it is organic, where the robot notices something. And I think what we're excited about is to really build flexible, fluid workflows. You want to get closer to where the humans interact than some kind of rigid warehouse architecture that's scripting everything. And the reality is the world's going to be a little bit of a hybrid, right? Where I would call it loosely coupled hybrid, where maybe there's a system that is controlled by the warehouse management, but then when it gets connected from here to here, the warehouse management system just says take it over to this, and that other subsystem notices it's ready and works autonomously. And so we think that um, it's interesting. I'm a large scale distributed systems guy by background and training, and in those worlds we have loosely coupled asynchronous systems, we have services, and we have tightly coupled synchronous systems. We've moved away from tightly coupled synchronous systems where we can to more loosely coupled asynchronous systems because they're more flexible, and so I think the same trend is going to happen in robotics, and increasingly happening in robotics, uh, where we're going to see subsystems loosely coupled and able to adapt more flexibly like humans would. And it's going to require less of kind of a fragile warehouse management orchestrator that has to get everything right every time.
I have one final question before we go to the rapid fire round. As we sit here in the mid 2024, what technological breakthroughs in robotics are you most excited about?
The So the biggest challenge we have in robotics right now is that uh, very high dimensional controllers. Say, the human hand has somewhere on the order of 46 degrees of freedom, right? The shadow mechanical hand has about 26 degrees of freedom. Trying to write the controller for those uh, is very hard. I mean, OpenAI did some very impressive early work with their learned dexterity models and their the and again, that's managing a 26 dimensional controller. The problem is there isn't a controls engineer who can really solve an open 26 dimensional controller. And if you get something wrong in an LM, maybe it spits out some hate speech or something. If you get something wrong in a robotic controller, the if it's a balancing system, it probably falls over, right? If it's a grasping system, it might crush the thing that it's. So so we need very robust controllers, and we need to know that they're generally safe, and that reduces the dimensionality, right? That reduces how many degrees of freedom we can build those control policies. And so if you look at a quadcopter, 4 spinning blades, maybe 6 IMU, like it's fairly constrained. Even like landing a 787 is not that many different degrees of freedom that you're trying to control, far less than controlling your hand. And so what I get excited about is, as we uh, develop more, as we can collect more and more data, there's just kind of this chicken and egg problem, which is we don't have enough data to really train we don't have 13 trillion tokens of robotic motion, right? Like we do text on the internet. And so we, and, and so there's this question, how much can we do without that amount of data? And then how are we going to get that data if we can't do it? So that problem is really interesting because once we do solve it, once we could have something with the dexterity of a human hand, like I give this example all the time, right? It's AirPods, right? How do you even open this thing, right? Like we teach each other, oh, you flip the lid, right? But then as you look at how you extract it, if you try to just grab it on top, you can't get it out. You learn eventually that you put your thumb here and you pull it out and you transfer it over to your thumb. It's a very, very, very hard thing for a robotic manipulator. Oh, and by the way, we have incredibly sophisticated touch sensors in our fingers and we just do it naturally. We don't have that quality of touch sensor either. And um, so to me, that dexterous manipulation, that bimanual manipulation, as we get that capability, robots are going to be able to do incredibly sophisticated things in the real world. But right now, you can see that cable behind, it's like an Ethernet cord. Asking a robot to extract that Ethernet cord and push that little tab and pull it out. We don't have that capability. And so I get really excited about what robots are going to be able to do when they have that capability. But I also think we're still a little bit out from there.
That's amazing. Actually, it's an incredibly at this point it's a hard problem, but I think it can unlock so many things. So that's wonderful. All right, with that, we're at the rapid fire round. I'll ask a series of questions and would love to hear your answers in 15 seconds or less. You ready? All right. Question
Sure.
number one: what's your favorite book?
My favorite book. Uh, there's a children's book, Mike Mulligan and his steam shovel. It's still my favorite book. The Yeah, rapid fire. We'll keep going, but there's a reason.
All right. No, let's hear the reason.
Well, the book is about how the steam shovel gets antiquated and then becomes the furnace for this building in the city. And I would say my biggest lesson from that is like never build yourself into the architecture. I still want to be out doing work in the world. I don't want to be. And so I've looked at that from a career lesson, but also from a technology standpoint. How do you build flexible building blocks, or how do you build your career so that you're not locked into just one thing that's rigid and immovable. How do you build that flexibility into your engineering, into your career, into everything?
I love that. Glad we dug into the reason on that one. All right, next question. What has been an important but overlooked robotics trend in the last 12 months?
But I think what people are the use of imitation learning to learn new tasks very quickly with some of these end-to-end models is super impressive. But I think most people don't understand that it doesn't generalize yet. We can learn new tasks very, very quickly, and they make really impressive videos and demos, but it doesn't generalize. So it's both really exciting progress and kind of misleading as to how much progress we've really made.
What's the one thing about robotics that most people don't get?
That robotics is deploying robots is very, very hard, and it is change agent work. You need a whole organization to embrace it. You can't just have a department somewhere trying to bring in a robot. You need to get the whole organization behind things. And that kind of change leadership. What happened in SaaS is we learned how to just product led growth, adopt things very quickly, and kind of bypass all that. Robotics isn't like that. You have to get everyone involved.
What separates a great robotics product from a merely good one?
I think the great robotics really think hard about not how the robot gets the task done, but how do humans experience the robot? Um, you know, Roombas are great, but those early Roombas kind of randomly wander around. Like it isn't really what you want. You want something that kind of goes in a more, predictable. And so, it's taken more development to do that. But I think we don't think enough about how the humans experience the robot.
What have you changed your mind on recently?
I changed my mind. Um, I think my timelines for how soon we might get very, very highly capable learned controllers like bimanual manipulators has come in significantly. I think I was in the kind of 10 to 15 year window, which by some folks was still wildly optimistic, and I think it's shorter than that now. I don't know if it's 2 years or 6 years or 10 years, but I don't think it's 15 years anymore. And so yeah, and we're doing things at Cobot assuming that those things are going to come along sooner and making sure that we have the robot that can take advantage of all that.
What's your wildest AI prediction for the next 12 months?
AI prediction. I think we're going to see maybe some kind of step function improvements in reasoning. That's my hypothesis. And I think it'll be similarly mind blowing when we do have that.
Our final question. What's your number one advice to founders who are starting out today?
I mean, it's a long journey, so make sure that it's one you're really, really excited about. And then if you're really excited about it, just go do it. Like, don't worry about what everyone else says. If you're excited about it, if you believe in it, then just go do it. But if you're not sure, I mean, Amazon, $1 trillion company, but like 20 years later, right? You gotta be excited about that 20-year journey. And so, but if you're excited about it, then go do it.
Yeah, that's an amazing nugget on which to end the podcast. Brad, thank you so much for sharing your insights here. Loved your wisdom and just the product building muscle that you've developed. I think it just shows, and I'm so glad that Cobot has a grand vision of building and deploying these robots. So thanks again for coming onto the show and sharing your insights.
Awesome. Great to chat.
All right.